Now that we've calculated the transition rate between any one state in the valence band and any one state in the conduction band, we can add all of these up to get the total transition rate. This is where Fermi's golden rule really starts to be useful. At first sight, it can appear to be a rather odd relation because in one way of writing it, it includes a Dirac delta function. However, Fermi's golden rule is really a relation that works when we have a dense set of possible transitions we can make. This case of optical absorption in a semiconductor is a good example of just such a situation. So let's see how this works. This expression here is the transition rate from an initial valence band state with Bloch wave vector kV to the conduction band state with wave vector kc equal to kV plus the optical wave vector. This is what we deduced in our previous work here. To get the total transition rate, and hence the optical absorption rate of photons, we're going to need to sum over all the possible initial and final states. The total transition rate, W total here, is formally the sum exactly over that. So here is our transition rate for a given initial and final state here. So we're summing over all the initial states and all the final states. So we can write that out here, and we presume for simplicity that this matrix element, PCV and the modulus squared of it, is approximately independent of K, which is a good enough approximation here. We don't need to make that assumption. We could have used a more sophisticated formula and left it in there, but this is good enough and will make it easier for our algebra here. So this is the sum exactly of what we wrote down before, this transition rate, just summed over all the initial and final states. We've taken this PCV squared out, and we're left with this double sum over delta functions. Now, we've shown above that for a given initial state with wave vector kV, the only final state possible is the conduction band state with wave vector kc equal to kV plus the optical wave vector. With this knowledge, we can drop the separate sum over the final states, because if we know the initial state, then the final state is defined for us. Since this optical wave vector and its magnitude is generally a very small fraction of the size of the Brillouin zone, we can now take a further simplification, which is that we neglect it entirely and we simply take Kc equal to Kv. Again, we could leave this in here. It would not make much difference to the final answer, and for simplicity in this algebra, we'll just take it out here, presuming we only take Kc equal to Kv and forget about the optical wave vector magnitude. This negligible size of the optical wave vector means that the direct optical transitions that we are going to get here are essentially vertical on the energy momentum diagram. Hence, for a given initial state Kv, only one term remains in the sum over the final states. And with our simplification here, that sum is the one in which Kc is exactly equal to Kv. So from now on, we're going to drop the suffixes v and c, at least when talking about wave vectors, and just use k. Hence, our total transition rate becomes this summation here over all the k values, and also now we're going to put in spin explicitly. The initial states are not just ones of different k values, they're also ones possibly with different spins, and there are two different possible spins. Now we formally rewrite this, and here we're considering unit volume, so these are transition rates per unit volume, in the following way. The sum over k and spin will be 2 times the sum over k, because essentially these transitions behave the same for the different spins, although they do tend to require essentially a related spin in the conduction band to the one in the valence band. But we're going to have 2 times the summation over the k values, and we're now going to use the result we just had derived in our previous section, which is that transitioning from a sum to an integral involves using the density of states in our integration variable. So the sum over k will turn into the integral over k with the density of states in here. Because at the moment our integration variable is k, or vector k, this is the density of states in k that we put in here. Next, we have to change variables in this integral to the energy EC of k minus EV of k, which is going to be the photon energy associated with a given transition. So formally, we're going to change from k as the integration variable to this quantity here as the integration variable. So, assuming parabolic bands, going back to look at our previous picture here for both the electrons and the holes, with effective masses here for the electrons and holes, and by convention we consider this kind of curvature, which would be a negative electron mass, we consider it as a positive hole mass. And hence we can define the transition energy, this separation between EC of k and EV of k, as the band gap energy, that's this separation energy here between the middles of these bands, plus these two portions of energy here, and one of them is h bar squared k squared over 2 times the electron effective mass. The other is h bar squared k squared over 2 times the whole effective mass, considered here as a positive quantity. And these will add up to give us this total transition energy, EJ. Now, we can think of a set of possible transitions here. So we can sketch this idea here. Here's a set of different possible transitions, each one of them going from a specific k state in the valence band to the same k state in the conduction band. And this is just some small portion of the Brillouin zone we're sketching here. So in this one-dimensional visualization we're using here, just for clarity of description, the transition energy EJ goes from its value at this end of my little sketch with wave vector magnitude k1 to EJ of k1 plus delta k, so this is some delta k along here, and this is the transition energy for this new value of k vector. In what follows here, we're interested in the number of different transitions possible. And what I mean by different transitions here is that this is a different transition from this one, and so on. And we want to know the number of different transitions in some small range of photon energies. So here we're going to be interested in the range of photon energies that corresponds to this energy all the way up to this one. So that's a range of energies, delta EJ, which is the difference between this energy and this one. And these are all technically in the vicinity of K1. I'm showing them just off to one side here for simplicity in this description, but they are energies in the vicinity of EJ of K1. Now, the difference in transition energies from one side of this diagram to the other is the sum of two parts. One comes from the electron effective mass and this bit of parabola, and the other comes from the whole effective mass and this bit of the parabola. We're going to presume this set of possible transitions is very dense. I've shown them somewhat exaggerated here with significant spacings between them, but in a real crystal they would be very close in energy. And they would have a density of possible transitions per unit energy near some photon energy, h bar omega. I've drawn the h bar omega as corresponding roughly to this transition energy. Perhaps you would prefer me to draw it corresponding to the middle one here, but it won't make any difference in the end because we'll be talking about very small changes in energy over some small range. And that is going to give us a total of this density of transitions per unit photon energy times this difference in energy between here and here. So here we could find, for example, there are 5 possible transitions within this difference between this energy and that one. this quantity, Gj of h bar omega, is known as a joint density of states. In fact, that's why I've put the J in there. Since it refers to transitions between states, it's not the density of any one set of states here, it's the density of transitions between states, and we call that a joint density of states. It's just a terminology. So we can write the transition energies here, Ej of k, which are just the separations between the conduction and valence band energies at this k, as this sum of these portions from the parabolic parts in both bands plus the band gap energy. And conveniently, we can rewrite that in the following form, where we define this parameter here, a reduced effective mass, which is just the sum of 1 over the electron effective mass times 1 over the whole effective mass, all with the reciprocal here. So instead of writing this, we write this term here. Then we can define our joint density of states as the number of transitions per unit photon energy, where we view Ej, the transition energy, as being a function of k. Now, like the energy density states in a given band, we can write this density of transitions per unit energy is going to be twice the density of states in K times the corresponding volume element in K space that corresponds to this range of energies here. And we've included a factor of 2 here for spin. So, because our expression for the transition energy has exactly the same form as the energy of K states in a given parabolic band, just with an effective reduced mass in here, we could now completely reconstruct the same argument that we used to go from density of states in K space to density of states in energy in a band. The argument would be mathematically identical in constructing the joint density of states expression here. So we're going to repeat this argument essentially, although we won't go through it, of how we used relations to get from the density of states in K space to the density of states in energy, but now we're going to use that argument for this new quantity here, which is mathematically in exactly the same form as the energy of states in a band. So with that, we can deduce the density of transitions per unit photon energy, which we now call the joint density of states, obtaining for photon energies greater than the band gap energy, that is Ej greater than the band gap energy Eg here, our joint density of states in this form. This is exactly the same form as we got for the density of states in a given band, then talking about the energy of states in the band. Now we've got this effective parameter in here, and we're talking about the density of transitions corresponding to specific energies. So this density of possible transitions also rises as the square root of the energy difference now between essentially the photon energy and the band gap energy, all raised to the power half of the square root. So going back here and substituting for this sum over k and spin, we have our factor of 2 for the spin here, our sum over k's, our integral over the density of states in K space, now transformed using the joint density of states of the variable Ej instead of variable K, using our result for the joint density of states, then we have the following expression. So that's just going from this summation form here to our integral form using the joint density of states. So now, finally, we can integrate to eliminate the delta function in this expression. We have an integral here with a delta function in it. Well, the integral with a delta function in it just gives us a very simple result. It pulls out from the integrand here the value of the integrand at this specific energy, h bar omega for Ej. And so now, finally, we have our total transition rate. It's some set of constants out here, an A naught squared, which is essentially the intensity of the electromagnetic field, the square of a matrix element, some constants related to the band structure in our parabolic case, and the square root of the excess energy, the photon compared to the band gap energy. Hence, we finally see how Fermi's golden rule can be used with an appropriate density of states to give us a total transition rate. We have got rid of that delta function in there to get to a useful result. To do that, we had to be working with a dense set of transitions, and that's what we've just done.